welcome to the Probability and Statistics course. Today's lesson is on confidence intervals for two samples. Last time we saw how to calculate confidence intervals when we have one sample. We saw how to calculate confidence intervals for a mean, for a variance, and for a proportion. Now in this lesson we are going to see how we can construct confidence intervals when we have two samples coming from two populations. So we are going to see confidence intervals for two samples, for the mean, for proportion, and for the variance. Now let's see why we need to make confidence intervals for two samples. So if we have estimators based on two samples and we want to compare the parameters of two populations from independent samples, and we want to construct confidence intervals for a combination of the two parameters, then we need to see how to do that by calculating confidence intervals when we have two samples. So what happens here is that we have two populations. Now we note here that we are talking about the same parameters from the two populations. For the moment we are going to talk about independent samples. Later on we are going to see what happens if the samples are not independent, and let's see how we can construct the confidence intervals for two parameters. We start by considering means. So as we said before, two independent samples from two populations. With mean we assume mu1 and mu2 respectively. Now the 100 times 1 minus a% confidence interval for the difference of the two means, when first of all we take the case where the variances are known, can be calculated using this formula here. We see that it has some similarity with when we have one sample. Here we take the difference of the two sample means. Again we use the standard normal distribution, and we calculate some combination of the variances of the two population variances. Now, the confidence interval for the difference of the means when the variances are unknown can be calculated in the case that the sample is large. We remember that we had the same case when we had one sample. We had to distinguish between, when the variances were unknown, we had to distinguish between a large sample, a small sample, the same case for two samples. So for this case, the confidence interval for the differences of the means is given here. It's the same formula as before, with the difference that we have replaced the variances with the sample variances. And here as well for the second sample, and we note here that we could have two different sample sizes. We do not require the two samples to be equal. N1 and N2 can be two different numbers. Also, the confidence interval for the difference of the means when the sample is small, but it comes from normal populations, the samples are small, but they come from normal populations, and variances are unknown but equal, we have that the confidence interval for the difference of the means can be calculated from this formula here, where S here is called the pooled estimator of the variance. We said that we assume that the two variances are equal. We're going to see how we can test this later on. And so we only need one estimate for the two variances, as we know that they are the same. So as the pool estimator can be calculated now using the formula shown here, where this is the variance of the sample variance of the first sample, and this is the sample variance for the second sample. N1 and N2 are the two sample sizes. Also, the confidence interval for the difference of the means when the sample is small from normal populations, variances are unknown but not equal this time, can be calculated by using again the t-distribution here, but the decrease of freedom k can be calculated is the smallest of the two numbers here, n1 minus 1 or n2 minus 2. So we choose as degrees of freedom for the t-distribution the smallest of these two numbers. Here the variances of the populations, we have assumed they are not equal, and so the same thing happens for the variances of the samples. We cannot anymore assume that they are equal, and so we use the sample variances from the two, calculated from the two different samples. Now, if we have two dependent samples, we have seen independent samples until now. Now we are going to see what happens if we have dependent samples. That means paired observations, that they come from one normal population with mean mu1 and mu2 respectively. The confidence interval for the difference of the means when the samples are small. Now for large samples we can substitute the t-distribution with the normal distribution. We have that. It can be calculated using this formula here, where the sample mean here is for the differences, and the sample standard deviation here is again for the differences. So we have assumed that we have paired observations. Now we take the difference between the values, and that's a new data set, which is our differences. Now for this new data set, for this new sample we have, we can calculate the sample mean and the sample standard deviation, and use this formula here in order to calculate the confidence interval for the difference of the means. Now, confidence intervals for variances. We assume that we have two independent samples from normal populations with the variances sigma 1 squared and sigma 2 squared. So we want to calculate the confidence interval for sigma 1 squared divided by sigma 2 squared. And we can use, as we can see here, another distribution, new distribution, which we see here for the first time. It's this F distribution. Now, F distribution consists of two different degrees of freedom. We can see that for this side, for the side here, the first degrees of freedom are n1 minus 1, the second is n2 minus 1, and on the other side we see that we take the value of F distribution, but we note here that the degrees have changed. First it comes the n2 minus 1 degrees of freedom, and then comes the n1 minus 1 degrees of freedom. Let's see an example. First of all, we have the time in minutes of two groups of engineers that takes them to assemble a number of machines. We see here group A, the first group of engineers, and group B, the second group of engineers. Now we have independent samples. That means that the two groups of engineers do not depend one on another. So if one engineer belonging in the first group took a long time to assemble a machine, it doesn't mean that this will affect the time it will take an engineer from the second group. Also, the populations are normally distributed. We assume it's okay to assume that the populations are normally distributed. Now we have small samples. As we have seen, our sample is less than 29. Now the question we are going to ask is if they have equal variances. So we want to construct confidence intervals in order to answer the question if they have equal variances. Now, although in this lesson we are not going to answer this question, the reason why we construct confidence intervals is in order, as we said, to make conclusions about what's happening with characteristics of parameters for the populations. So what we are going to do is calculate the confidence intervals here, and in our lessons, our next lessons, we're going to see how, using these confidence intervals, we can answer questions like this. So, for this example, we want to calculate the 99% confidence interval for sigma 1 squared over sigma 2 squared. Now we know the formula we have seen is S1 squared over S2 squared, the sample variances, 1 over F distribution n1 minus 1 degrees of freedom, n2 minus 1 degrees of freedom, and the upper limit, again the F distribution, this time with n2 minus 1 degrees of freedom, and 1 minus 1 degrees of freedom, A over 2. Now from the tables we can see that this value here is 4.15, and this value here is 3.58. Now, F distribution, as the chi-square distributions are not symmetrical, and calculating here this formula, putting in the numbers we have calculated, we find that the confidence interval, the 99% confidence interval for sigma 1 squared over sigma 2 squared is 0.243, 3.58. And so we have concluded that sigma 1 squared over sigma 2 squared is between 0.243 and 3.58. Now, let's think a bit about our question if our variances are equal. We are not going to show anything mathematically here, but we are going to try to understand what's happening with the confidence intervals and how they can be used in order to draw conclusions. So, if the two variances are equal, then sigma 1 squared over sigma 2 squared should be 1, or at least close to 1. So we would expect that if this happens, then we could conclude that sigma 1 squared is equal to sigma 2 squared. Now, if we go back to our 99% confidence interval for the variances of our data, we see that we are sure, 99% sure, that the real values, if we divide the two variances, the real value would be between 0.243 and 3.58. So we cannot say that they are not equal. We cannot say that because the value 1 is actually included in this interval, we cannot say that these two are certainly not equal. So we are going to assume that they are, and in order to calculate confidence intervals now for the differences, for the difference of the means of the two populations, we are going to use the formula where the two variances are assumed to be equal. So for this data, we can assume that the two variances are equal, and in order to calculate the 99% confidence interval for the difference of the two means, we could use the formula we've seen with the two equal variances. So we have t distribution n1 plus n2 minus 2 a over 2 s and the square root of 1 over n1 plus 1 over n2. Now we would need to calculate the pooled variance from the samples. We know that this is given the variance. We need to calculate the standard deviation. The variance would be given by n1 minus 1 s1 squared plus n2 minus 1 s2 squared over n1 plus n2 minus 2. We would need to estimate the two variances from the two samples, and this, if we do all calculations, is 28.83. Now, taking the square root and substituting here in our data, we have that the 99% confidence interval for mu1 minus mu2 is actually given by minus 30.03 to minus 4.45. So for this example, we have talked about independent samples. Let's see if we have samples that we assume they are not independent, what happens. Let's see an example. So now we have the time of the same group of engineers to assemble machines of make A and machines of make B. And the data are given in this table. Now here we understand that the data are not independent, as we would expect that an engineer that takes a long time to assemble one machine, he will probably take a long time to assemble another machine, and the other way around. So here our samples are not independent, they are paired, as we have said, and we would need to calculate the differences. So we have the first group of data, the second group of data, we take the differences, and we have here D is the new sample, the differences. Now we can calculate the confidence interval for the difference of the means using these differences, as we have seen, by calculating this time. We would have the sample mean for the differences, t distribution. We have the standard deviation, the sample standard deviation of the differences, and this, if we substitute the numbers and do the calculations, we find that is the interval minus 43.56 to 41.56. So we have seen two examples with two different sets of data. One, samples are independent, and the other samples are dependent. Reading the context of our examples of our problem, we have to understand to make sure that samples are either independent or dependent, and make use of the right formulas to calculate confidence intervals for the difference of the means. Now, we are going to see confidence intervals for two proportions. X1 is the number of elements in the group with a characteristic from first sample, and X2 is the number of elements in the group with a characteristic from second sample. We assume for the proportions that the samples are independent. And now, the same way as for one sample, we assume that the proportions can be estimated P1 by using x1 divided by n1 and P2 x2 divided by n2. For this case, the confidence interval for the difference of the proportions when samples are large can be calculated using the formula here. Now we are going to work through an example to calculate confidence intervals for proportions. Let's see. So our data were collected in order to research if the number of smokers have decreased between years 1989 and 1999. The data we have collected are given in a table. We have that in 1989, 1,500 people were asked, from which 498 answered that they are smokers. So N1 will be 1,500 and X1 will be 498. Now in 1999, 2,000 people were asked. We see that, as we said, we do not require the two samples to be the same size, but we require that the two samples are large. In this example, we have 1,500 people in 99 and 2,000 people in 2000, so the sample is sufficient in order to calculate confidence intervals. And for the people in 1999, 652 answered that they are smokers. So now, as we see here, we have two samples, and we want to see if actually the two proportions are equal. So in order to do this, the two proportions, we want to ask if they are equal. And this question can be calculated to find out if the differences are 0 or not. Now again, as we said, we are not going to answer the question. The only thing we are going to do is calculate a confidence interval for the difference, because later on in our other lessons we are going to find out, to learn how to use these confidence intervals in order to answer questions like this. So here, first of all, as the two proportions are not known, we need to estimate using point estimators. Now, a point estimator for the first proportion will be given by x1 over n1, so it's 498 divided by 1,500, which this is equal to 0.332. Now, the second proportion, a point estimator again, we have x2 divided by n2, which is 652 divided by 2000, which is equal to 0.326. Now, the numbers we see here, of course, we cannot answer the question. They are not exactly the same, but we do not know if they are close enough in order to say that the two proportions are equal, or if they are not close enough in order to say that the two proportions are equal. That's where we actually need statistical methods to answer questions like this. So confidence interval are needed to be calculated here for the two proportions here. We have that. The 99% confidence interval for the difference in the two proportions. As we've said, it's given by the formula here, again the standard normal distribution, and we need to calculate, knowing the estimates here, we need to do our calculations in order to find the interval. So for this case, we have that. This is actually equal to minus 0.0205 and 0.0325. Now, again, for this example, we see that our 99% confidence interval actually includes the point 0. So, looking here, we know that we could say that number 0, it is a possible value for the difference of the two proportions. This is a possible value, and actually it is possible that the two proportions are equal. Now, we can then conclude, making some conclusions from the confidence intervals, that the two samples come from populations with equal proportions. And so we can answer our initial question: if the number of smokers have decreased, that no, they have not decreased. Now we are going to see all these, how to answer questions in more detail in our following lessons. In our following lessons, we are going to see about hypothesis testing. Hypothesis testing is what we have seen here, questions that need to be answered. Now, hypothesis testing is related with confidence intervals. We are actually going to use the confidence intervals in order to do hypothesis testing. So we would need to make clear that we know exactly for each data set which confidence interval, which formula we need to use, if our samples are small or large, if they have equal variances or not, and so on. Now, so we conclude our lessons in confidence intervals for having seen what happens with two samples, having seen what happens for differences, especially differences of means, for two proportions, and finally for two variances, for sigma 1 squared over sigma 2 squared, which actually it's very useful in order to answer questions like if two variances are equal, in order to know which formula for confidence intervals for the differences of means we need to use. For more information on this lesson, you can visit the webpage of Netuno MedNetU project.